Welcome to another tech day live from my bedroom slash workstation. What I have planned for today is to continue with the chapter on training linear models for machine learning. So let me just see what we have here. We have something called regularized linear models, which I have no idea what the title means. So hopefully what I can do here is, so the concept of regularized linear models is closely related to the concept of overfitting, which means that regularization is saying, okay, don't go crazy with the blocks, keep them small and neat. Small and neat. All right. So we have three types of regularizations. We have ridge regression, lasso, and elastic net. Okay, so what does the book says? A good way to reduce overfitting. Okay, now, what's overfitting? What is overfitting? A good way to reduce overfitting is to regularize the model, which means to constrain it. The fewer degrees of freedom it has, the harder it will be for it to overfit the data. A simple way to regularize a model is to reduce the number of polynomial degrees. But first of all, what's overfitting? Where's my tablet? It should be here somewhere. Yeah. So we have regularized linear models. I haven't said that word correctly once during this whole stream. But okay, there's a concept called overfitting that I'm gonna explain it right now. So overfitting. Again, ChatGPT is giving great examples here. Imagine you're learning to cook spaghetti. Okay. And you make it for your friend, and your friend, hopefully I didn't draw anyone famous, and your friend says, okay, I love when the spaghetti is super salty and the noodles are extra soft. So the next time we cook spaghetti for our friend Alex, we cook them just like they want. It's super salty, it's soft. And you measure the salt like into the milligram, you measure the salt. But now we are serving the same noodles to another one of our friends. Let's call him Jordan. And he hates the noodles because Jordan doesn't like salt at all. And that's basically overfitting. We are trying to perfectly match one person's taste that we forgot to cook spaghetti for everyone else. In machine learning terms, it means that, okay, our model is learning from the training data. If it memorizes the training data too perfectly, it won't do good on new unseen data. And that's overfitting. Model learns from training data. Okay, model learns from training data. If it does too well on training data, it won't do good on new data, and that's basically overfitting in a nutshell. So we will have low training errors, which means it's great performance on the data we already know, but we will have high validation errors, which means it's gonna perform poorly on new data. So yeah, overfitting happens when our model is too complex and starts capturing random noise or, you know, some specific quirk of the training set instead of real patterns. And that's basically the point of it. If our model is trying too hard to be perfect, we can calm it down by putting rules or limits on it. And now that's how we solve overfitting, by regularization. Yeah, I said it. I said it correctly this time. So for example, if we have a model which looks like this, so y, this is the base, bx times cx squared times dx cubed times ex to the fourth, we can regularize or simplify this by removing the high powers. We can simplify it by leaving only this a bx plus cx squared, which makes the model simpler, less flexible, and less likely to overfit. Okay, now I'm gonna hit ridge regression, and I for some reason this will have a lot mathematics. So if you are bad at it like I am, let's get ready for some real head scratchers here. Okay, so let's look at the code here. Okay, so this generates a random seed. We have 20. Oh, I need to run everything above. There is no NumPy library here. Okay. Man, I bought, initially I had 2 sticks of 8 gigabytes of RAM, and the notebooks were running relatively slowly, I would say. And now I got 2 new sticks of 32 gigabytes each. And for some reason, it still doesn't... It's not instant. I want it to be instant. How did our forefathers work on those old clunky machines? Okay, is it working? It is working. Okay, 20... What's this? 20 items. We have an X, we have a Y. Wait, what's being done here? Let me check. Print X, print Y. These are most probably, yeah, vectors, and they were generated randomly. What else do I have here? Wait, where's my tablet? Okay, just a second. Random seed, I won't even comment on. We make sure that the random numbers are the same every time we run the code. That's what MP random seed does. Now, 20 makes 20 data points. Now, the X will generate 20. First of all, this will generate 20 random numbers between 0 and 1. And it's gonna multiply them by 3, which means that it's gonna scale all numbers to be between 0 and 3. So we are creating 20 input values. We're gonna have a vector that will contain values such as 1.2, I don't know, wait, 1.2, 2.7, 0.5, and so on. And we are gonna generate 20 of these in this vector. Ah, here they are. So we have 20 of these. 1, 1, 2, 8, 2, 1, 9, blah, 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 2, 9. So from 0 to 3. Now, y is our target value. What kind of data will it create? What kind of formula is this? So it's y is equal to 1 plus 1/2, because it's 1/2 x plus, it's creating a random number between 0 and 1 and it's dividing it by 1/5. Okay, this is usually used to create noise. I don't want to make the target value too perfect, because we need to train on it. So this will create some noise, but why is it dividing it by 1.5? Why is it dividing it by 1.5? Oh, there are 3 people watching this. Thank you, thank you, thank you. I don't know why you do this. I'm not an expert in this. But if you want to watch me struggle understanding why is this divided by 1.5, please do. Okay, so ChatGPT says, okay, this will create some noise like we did in some snippets above, but this will regulate the noise a bit better. It's gonna reduce the noise so it's not overwhelming. And why we haven't done this before? Okay, this will create from 0 to 300 numbers. Reshape what is turning them into columns. So if I run this again, and if I run this below, okay, I plotted X and Y here. I plotted X and Y here. Hi. Yeah, I'm funny. I plotted X and Y here. We import ridge. Oh man, what the fuck? What will we do with the linspace that we created with these values here? Will we ever reuse them? Wait. Let me get some theory on what this is before I even continue looking at this. Okay, until now I know this first snippet. There is a pretend dataset. Like, I don't know. We draw a line with a shaky hand or some bullshit. And we want to train the model that will know, okay, the model will understand what the pattern between this is, hopefully. But what is ridge regression? What is ridge regression? Let's say I have these same dots here. Bam, 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 bam. Wait. Here they are. Bam, 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 bam. Okay. And I want to draw a line, okay, that will fit all of these dots. Linearly, what does it mean to solve this via linear regression? Is to just draw a line like this, and the line should be approximately at a decent distance between all of these points. That's linear regression. But what if we have all of these same points, but instead of this line, let me put another color. Instead of this line, I do something like this. This basically means that the line is bending and stretching to touch every dot exactly, which ties into the concept of overfitting that I explained back then. So what we are doing, we are using this ridge regression to say, okay, don't do this too far, don't overfit it, keep this tidy and small. And the difference is, so the regular linear regression. The regular linear regression is trying to minimize the error between prediction and actual values, and it uses MSI, mean squared error, as a cost function to minimize this line. Basically, what MSI says is nothing more than the distance between the line that we are solving that we created to solve all of these points and the points of it. So the smaller the distance, again, we can fit every one of these points, but we should reduce the distance and the line should be, okay, I messed up. And the line should be straight. So we won't fit all the points, but we should fit them optimally. But what the ridge regression does is it tries to minimize the error and keeps the weights small. Oh, it must be fucking kidding me. What does this mean? What does this mean? Where is the formula for this? We are adding a regularization term equal to something to the MSI. And this will force the learning algorithm to not only fit the data, but also keep the model weights as small as possible. Okay, so for ridge regression, we are using the same thing. We are using the mean squared error. Okay. Hey. Thanks for joining the live. I'm trying to learn and grasp machine learning as a concept. And currently, so basically, I'm trying to I'm a web developer, I'm a software engineer, and I'm trying to switch my career, and we are all gonna be booted by AI sooner or later. So I thought, okay, let me maybe join the enemy, and that's what I'm learning. And this is basically not only using LLMs and all of these AI models that are freely available and have an interface open to users. This is like all of this heavy math. Basically, right now at this point, we are trying to train linear models to solve examples, and I'm gonna do one of these for ridge regression right now. So if you stay, maybe you can find something interesting. Maybe I can find something interesting as well, hopefully. So this is the cost function. So, and I multiply it by alpha. So I don't multiply it. This is my mean squared error plus alpha. Yeah, I am. It's self-study. I finished university a couple of years back to be a computer scientist. So I'm not studying from teachers. I have this book that a lot of universities use, and I'm just going step by step. I'm trying to cover the whole book for machine learning. Again, this is something that I'm planning to do just to get bread on the table. My real dream is to build a game. And also I installed Unity as well, so maybe I'll do some Unity later on. Sum of squares of weights. So this is the regularization term. And that's the only thing I assume what defines ridge regression, that you have this regularization term. Hey, welcome. I'm a student from business background. Okay. What do I have here? So we try to minimize the error and keep the weight small. And we have this regularization term. And we have a ridge regression cost function, which looks like this. J of theta is MSI of theta plus alpha over M. What the fuck? And the sum of I of all the thetas of square. Wait, can I do an example of this? And I learned C and Python. Man, C and Python are the best languages to learn. For some reason, the idiots at my university gave us only while I was studying. So in the first year, we only had like one semester of C, and then they said, you know what's really popping off? Web. So let's from the second semester of the first year, let's mostly do JavaScript, and we did Python and C, but for niche classes like data mining and stuff like this. All the big, I would say big classes, but okay, introduction to programming was C, advanced programming was also C, actually C++, and then project building was JavaScript. We have web development, which was JavaScript, software engineering, which was okay, it was Python, but we also had to use a front end, so it was also JavaScript. Like learning Python and C is really good. I think. Okay, let's do a tiny data example of this, because I also don't understand how this works. Okay, let me just move to a new page. Let's say I create a new X, and X is an NumPy array. So it's not a regular array, it's a NumPy array. 1 1 1 2 1 3 1. No, let's change this a bit. So let's make this 2 2 2 3 3 5. And I have the target values, which will be again an NumPy array, but it's gonna have, let's say, 5 7 9 11 and 15. Okay, so why do I have two values here? Because these are two input features per row. I don't know, let's say how many, one of them is how many times we spent working on something, and this is how many cups of coffee we had to produce, how many points we have on an exam. I don't know, let's say this is it. So then I can pull up a linear regression model, and I can fit it on X and Y. Okay, wait, let me do this about here. Code. Okay. So I have this. Okay, we had some technical difficulties. I apologize. I really apologize. For some reason, it just stopped. Welcome back. There's anyone here. Welcome back. So I have X and Y. I have the two input vectors here, input features, like as I said, time spent and I don't know, amount of coffee drank to get points on an exam. Okay, I think I have already lin reg is what? Linear regression. I already have it. Lin reg. Let's fit it on X and Y. Coefficients. No idea if this is correct. So let me print out coefficients. Okay. So I have coefficients. If I run this, okay. These are the coefficients. And now if I print the intercept, these are basically the solutions to linear equations. Interception. Hopefully it won't be jittery and broken. Yeah, this messed my whole conception now. But all right. So if I print this again, I have the solutions to this list of linear equations. I've been given weights for each feature and the bias, which is the y-intercept. And it prints, let's say, 2, 1.5, and 2 here. So our model in this case, because it print out this, is going to be 2 is 2 times x1 plus 1.5 times x2 plus 1.95 or 2. I also misspelled intercept, doesn't care. Okay, but now I need to fit ridge regression, and this time I need to fit it with regularization. So here I'm actually importing all of this, but let me just copy this. This is a test snippet, so it's not from the book, it's something that I've been doing. Okay, I'm gonna copy this here. I'm gonna put the alpha to be, I don't know, 1.0. And then I'm gonna fit this on the ridge regression. And what now? What if I, instead of the linear regression here, I use ridge reg? Oh, we have 2 people now. Yeah, sorry, we had some technical difficulties if you came from the old stream. I'm basically trying to, the way how I learn best, personally, is to do a bare bones example of the problem, simplify it. Like here, I have this X matrix and the Y, the list of solutions, and I'm trying to do this step by step. Okay, so coefficients, intercept, what's the difference here? And what happened here? So ridge did something behind the scenes. It shrank the weights to make the model simpler and more stable, which will be less likely to overfit. And let's say we have a new input. X new is gonna be numpy array. What I will have 2 and 4. And now if I print linear prediction, it's gonna be linear regression, predict me x new, and I'm gonna do the same for ridge. Hey, ridge. Sorry, the old stream just collapsed on itself. I don't know what was going on. If you just joined, what I'm trying to do, I'm a software engineer. I realize that the machines are taking over, so I'm learning all of this machine learning crap in order to be a good slave to them. And right now, apologize, I drank some water. Right now, I'm at a point of being totally mocked by by ridge regression predictions or whatever this is. I'm doing a really simple example of it. What happened now? Where the hell? What happened? Oh, okay, I collapsed it. So if I run this again, hey Faisal, welcome. I love your avatar. Yeah, NumPy is fun. I had to I spent like 2 weeks like deprogramming my brain from thinking of regular arrays when seeing these. I had to slap myself on the face. Okay, these are matrices. These are okay. Yeah, the Giga Chad. Okay. So the ridge prediction just gives, oh man, it just gives us the same crap. It just so the linear regression tries to fit the best line, but ridge regression is 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 trying to say, okay, don't go wild with whatever numbers we have here. Do you want to plot this or to go with a real example, or maybe to, okay, let's go further. So I'm gonna comment all of this, and here I'm running the ridge. Where is it? Here I'm running the ridge regression again, but on real data. Okay, what if I go above? X has 1 feature, but ridge is expecting 2 features as an input. So I fit these values for X and Y, and then it predicted a new value, which will be 1.55. And this, I think, will just draw the, yeah. So what's going on here? What's going on here? Okay, I create a plot. I create a subplot. I'm plotting what is the ridge. What the fuck is the ridge? Plot model ridge. Okay, but where do you pull the ridge from, brother? Plot model. Okay. This is the class of the model. I completely missed this whole fat method right here. Okay, so this will just generate a plot showing the effect of ridge regularization. Okay. So we'll have linear regression, we'll also have polynomial regression as an example. So, okay, this just generates the plot. This is a wide figure. We have the left plot. Here I'm creating the plot using the plot model. I'm gonna go back to the method to maybe go over it as well. Okay, Y label, this is the right plot. I'm using the same thing. Okay, here I'm providing the alphas. Axis, Y-axis, set tick labels. No idea. I think it's just a configuration. Step for plots. I don't think this is important, but okay, it just creates these two figures here. What are you doing, you big fat asshole? What are you doing here? Okay, I'm plotting X, Y, blue dots. Okay, it's using blue dots. Line width 3. Okay, so these are my points here. All of these blue dots right here. If alpha style in zip. Okay, so it's pulling this. What is zip? Is this a method? Zip object yields and length tubes. Okay. So this most probably, because we provide the alphas here, it's a tuple of 3 elements. This is also a tuple of 3 elements, so you're gonna pick each one. So alpha of 0 will have blue. Is this blue, green, and red? Yeah. So alpha of 0, and you can see here in the legend. So we are just iterating through this, and the first one is gonna be 0 with blue dot line. Then we'll have green line. Then we have just a regular line here. And the alphas will match to every one of these. Okay. If alpha is greater than 0, no, I don't. If alpha is greater than 0, I have a model here. And I'm an idiot. Okay, if alpha is greater than 0, I'm using the model class that I'm provided. Actually, I'm using ridge. I'm creating the alpha, I'm creating the arguments. Otherwise, let's just do linear regression. Plot model, how many times have I called this? Only 2. Otherwise, let's do linear regression. If there's a polynomial, like I provided it here, let's create a pipeline with the polynomial features of degrees. Standard scalar, I don't know what standard. Then we fit the model, and then we predict with the where's 6 new? Where? Then we predict the value. Where is 6 new? It's here somewhere. Where has this come from? X underscore new. I thought. Okay, so this is just a method that iterates through all of these options, checks if alpha is greater than 0, does some logic. If we provide a polynomial, we create a polynomial pipeline. We fit the model on x and y. We predict the model on the new value, but I have no idea where this new value is. It's here somewhere. It must be here somewhere. Where is this created? X new. All the way. Ah, here. Okay. So I'm predicting when I'm on multiple values. I'm predicting the new y. I'm plotting all of this. These are just configurations. Model class. Am I using the model class again? No. So these are the points, the blue dots. The blue line. The blue line is the alpha of 0. Plot model. The blue line is the alpha of 0, and if alpha is greater than 0, because it's not, I'm creating a linear regression here. Okay, so I'm creating a linear regression, which I assume is the blue line. Now the green line is 10. So alpha is greater than 0. We are calling our ridge class right here. This is the green class. We have the alpha of 100. This one is a bit broken or not okay. So blue, green is a bit more conservative. The same thing here with the polynomials as well. If the alpha is 0, we are calling it linear regression, but I also provided a polynomial flag as well. So I'm using linear regression, but I have these pipeline steps here to take care of. So this is the blue one. The green one is a bit more conservative. And the red one, again, is just broken. Wow. I actually somewhat think I got this. What about you guys? I think I'm getting this because as we increase alpha, again, I have no idea what alpha is. Alpha is a black box in my mind. As we increase alpha, we are getting a more flatter line. Okay, the book also says that with linear regression, we can perform a ridge regression either by computing a closed form equation or performing gradient descent. So this is a gradient. This is the same thing, only using gradient descent. The same thing as above. it does everything the same. Has it predicted the same value? 5532 5530. Okay. Yeah, we use the gradient descent here. Oh man. You know what's the worst thing? I spent, I think, another hour learning about gradient descents in this exact chapter, and still now I came across them, and it took a minute for me to like, oh, what the fuck is, oops, what the hell is a gradient descent? It's important to constantly uh no, retrain is not the right word. To if you are learning a concept, I think it's really important to keep those memorization cards, and these things I found ridiculous back in the time, but it happens. Okay, so the book mentions gradient descent, and man, I have no idea what's happening here. What else, man? What are you doing? Slow shows the closed form solution of ridge regression compared with the net. Okay. Ridge regression, I think I got it. But I want to do a real example. Something simple now. I have a calmful voice. Thanks, man. Thank you. I um what kind of app are you building? Software as a service? What kind of, I mean, if you can speak about it. And regarding my voice, I always thought that people don't like my voice or don't like hearing me. But this is the only way I can study, like by talking to myself. And I realize why not stream it as well? Okay. This is the ridge regression. Let's do another example. Like a really simple one. I think the book over explains this bullshit. I think they really went above and beyond in order to confuse you as much as they can. I really have a problem with textbooks, and I realize that now. And I know there's a great little point where this vastness of textbooks and comprehensiveness of textbooks meet with the basic stuff you find on Udemy. Man, that sounds really cool. Series which can be easily done through AI, ML, like data visualization of word surface data. So what are you doing, like certifications or something like that? Like these, when they draw mountains, like you have the outer layers being different color, and as you approach the summit, they're becoming more and more colored in a different way. Is it something like this? I don't know how it's called. I'm sorry. Okay, how to fit a model. Again, let's do the same thing here. I'm gonna do the smallest example here. MP array. Bum. 1. The same thing here. MP array. 2, 3, 5. Oh, is this okay? Why is this one wider than this? I have 3 R's here. Okay. So we don't have two features here. So the formula is only ax plus b. So I'm trying to find x. No, I have x. I'm trying to find a and b. Plane linear regression. Plane linear regression. Okay, what is the goal of plane linear regression? Is to minimize what? The error. So it wants the smallest possible error using the MSI. Oops, using the MSI. And I have somewhere the formula for MSI here. But actually, let's just find it online. MSI formula. It's the mean squared error. Yeah, and this is the formula for MSI. I'm going through the whole data set. I'm dividing this by the number of data points. And I'm subtracting my value from the predicted value. I'm squaring it. I'm dividing it by the number of data points. And this should be my mean squared error. And linear regression. No. Okay. Lin regression fit x, y. And now I'm printing the linear coefficients, lin reg coefficient, and I'm gonna do the same for interception. And by the way, coefficient, and let me just show you this, because this is what, again, this is what I don't like about textbooks, because A is the interception, is the empty value. B is the coefficient. It's the value that is related to an unknown, and we can have multiple of these. Is there another image here? No. So basically, when we are saying, oh, interception and coefficient, where is this? Oh, it's here. Interception and coefficient, I'm only asking for the values of A and B and nothing else. So we are gonna have a model that will be 1.5x, because these are the coefficients, they could be multiple of them, plus 0.33. This is a linear regression. Now, a ridge regression uses a different cost function. Instead of MSI, it's going to use a different one. Let's ignore the math for now. But basically, the formula for ridge is it theta? I hope it's theta. It's MSI, so it's the formula we have, plus alpha plus v squared. So alpha here is a value used in ridge regression, which is a constant that multiplies the term controlling regularization strength. Basically, based on the alpha value, we can reduce the weights of our coast. I always have like 4 or 5 viewers and no one speaks. Maybe people just leave me up in the background, which, I mean, it's a compliment that people think I have a nice voice. Maybe I should start eating carrots on an ASMR channel or something like this. By the way, next time when you and the other 2 viewers don't have any work. I always wanted to teach peoples, and I don't know. I would like to see if you can follow like what I'm trying to explain. The way I'm understanding it and the way I'm teaching it to someone. Being a teacher is a really noble profession. Too bad teachers are really paid like incredibly shameful salaries, man. Okay. So what do I have here? I have my predictions. Let's say, wait. Lin, reg, no. How can I print the prediction of this? Ah, okay. So, wait. Where's my tablet? Maybe I can write this better. Okay. So, I found the coefficient and interception. So it's 1.5x plus 0.33. And then based on the input of 1, 2, 3, which is the NumPy array, I get, if I plug this in for every one of these values, I'm gonna get a y predictions of what? 15183 15 times 2 plus it's 3 plus 0 is 3.33. 3 times 1.5 it's 4.5 plus this, it's gonna be 4.83. But these are the predicted values. Our true values are 2, 3, and 5. So we have our errors, and the errors are the values that we subtract from here. So the error will be minus, okay. The errors will be minus, so I'm subtracting the predicted value, I'm subtracting the predicted value from the real value. So it's gonna be minus 0.17, it's gonna be 0.33 and minus 0.17. Okay. Next, I can calculate mean squared error, and I'm calculating this by, I have 3 data points, so I'm dividing all of this by 3, and I'm multiplying this by this value squared, so it will be minus 0.17 squared. The other one is going to be 0.32 squared, and the third one is going to be again 0.17 squared. Oh, when it's all add and done, it's going to be 0.055. Okay, so this is the MSI, but then I also have the ridge cost, which is this value that we just produced here, plus 1 is the alpha, multiplied by 1.5 squared. 1.5 is the first solution that we got, and it's related to x. Sorry, and it's here, it's glued to x. So I'm gonna get a pretty big number here, I assume. 2.305. So if I provide alpha here, and if I provide a big alpha like 1, the cost of the ridge is bigger than the cost of MSI. But what if we decide what the best value is with regularization. Okay, I'm just gonna copy this. I have no energy left in me. Reg. It's gonna be a ridge. I need to provide a ridge. I need to provide alpha. Alpha is 1.0, and I'm fitting it against x and y. And I'm gonna copy all of these coefficients here, and instead of linear, I'm gonna say ridge. Instead of linear edge, I'm gonna say ridge edge. Ridge edge. So I get a different value. So the ridge reduced, ridge reduced the slope from 1.5 to 1, and it increased the intercept. And now I can draw both of these. X, range, numpy, line space 0, 400. Reshape -1, 1. Okay, let me just get the predictions here for linear and for ridge. Let me just create the plot, scatter. Wait. Scatter. I'm just gonna copy this again, but instead of I'm gonna have plot here, and it will be the range, and it's gonna be linear solution. I'm not gonna have a color here. No. It's gonna be blue, and label is gonna be linear. And if I plot the other one, I'm gonna, why is it, where? Aha, I'm missing here a comma. I'm missing here a comma. I'm doing the same here, but instead of linear, I'm gonna use ridge. And it's gonna be red for the ridge, and the label is gonna be ridge. What if I run this now? Oh, this looks so simple, but yeah, basically we are just, oh man. When I said I wanted a simple example, this one is really simple. So it's just another way of solving linear regressions, but why is it better than linear? I think that's it. It was really underwhelming once we got away from all of this bullshit in the books. But we can use ridge regression when features are noisy and when we overfit easily. I think that's the main use case. Again, I'm a novice here, so I don't have the experiential background in order to explain you why and when this would happen, and maybe proper examples in which they would happen. But basically, what ridge does is just reduce overfitting. When we have many features, when the data is noisy, when we are doing polynomials, let's say. So, yeah, what's this? This sounds interesting. Yeah, this looks really cool, but okay. What's the time for me right now? Ridge regression. Oh, well, this one is even worse. I apologize. I forgot to turn off my phone. This one is even worse. Maybe I'll do this for the next one. For the next video that is. What I want now. Ah shit, I have no time to do my video game stream. I'm gonna do it the next time. I really apologize, guys. It's relatively late where I'm from. I just wanna play some games and get early to bed because I'm working tomorrow. I don't thank you all for watching this video, and I hope you learned something. I hope also the sound of my voice in the background is calming enough for you. Thank you all, and see you in the next one. Bye.